So the last topic I want to cover in this particular section focuses on the order of results for the operations that we're performing, which, as you know, can be intermediate operations, terminal operations, and so on. Once again, we're going to look at some examples here from the EX21 folder in my GitHub repository, so feel free to follow along. Let's talk first about how different intermediate operations can affect the order in which the results are produced. So once again, we're going to start off with our input. So the input here, as before, is an array, and we turn that into a list. So we have an array, 2, 3, 1, 4, 2. We turn that into a list, so we have a list of integers. And then we're going to do things a little bit differently than we had done before. And in this particular case, you're going to see that we take that list, we turn it into a stream, and then we say, I want the elements in this stream to be distinct. Now you can see by default, or with the original contents in the input, the elements are not distinct. They're duplicated. So 2 appears twice, for example. Distinct is a so-called stateful operation that's going to go through the elements in the stream and then make sure that there's no duplicates. Once we do that, we're then going to go ahead and do the filtering and the mapping and so on. But we're going to restrict ourselves to just S output limit number of elements. So that's another intermediate operation that's going to affect the behavior of our system. So we're going to get no duplicates, and we're going to limit ourselves to just the first number of elements that we have here. So the encounter order, of course, is 2, 3, 1, 4, 2. And then we go ahead and remove any duplicates by using distinct, which is this stateful intermediate operation. And then we also use limit, as I talked about before, which is another stateful intermediate operation. So there's a couple of different things we're showing here. Now, the results of this particular computation are going to be 4 and 8. However, it's likely, especially because we're running this as a parallel stream, that the actual performance of this is going to be fairly slow. And that's because limit and distinct are stateful operations, and we're using them in a parallel stream, which means that all of a sudden there's dependencies between the different computations. So this is no longer really an embarrassingly parallel computation because there's state that has to be maintained. And so that's going to introduce extra passes through the computation in the pipeline. And it also means that it's got to keep track of how many things have been seen. So that gets more complicated, and therefore it means that the code is going to be slower. So even though the output is ordered in the way that we'd expect because of the encounter order semantics of a list, the behavior is going to be kind of slow. One thing we could do to speed things up while still keeping the other properties is we could go ahead and throw in another intermediate operation, which is the unordered operation. And what unordered says is, I no longer care whether the output is going to be ordered in encounter order. So it could come back in whatever order it happens to complete in based on the other processing. So it'll turn out that this way we're going to use the unordered operation, which means that it's now non-deterministic, the order that the results will come in. It could either be 4, 8, or 8, 4, or whatnot. And it's also going to be faster because it no longer has to preserve these ordering dependencies across the parallel computations. So chances are this code will be faster, but it won't be as deterministic in terms of the output order, which may not matter, of course. So as a result, you could get either 8 followed by 4 or 4 followed by 8. Now, obviously, for something as simple as a list with a couple of elements in it, this is overkill, right? You see the real interesting results when you have lots of elements that you're doing and processing large amounts of input that might have long computations on each element. So if you actually run the examples in the EX21 folder, you'll see that they have much larger numbers of elements than just 2. I limited it to this small example so it would fit on a slide, and I could talk through it and help you understand it intuitively. But in practice, the real bang for your buck comes from having much larger amounts of input. It turns out that there's also terminal operations that affect the result order as well. And let's take a look at some examples. I've alluded to this earlier when we talked about terminal operations, and we talked about terminal operations that don't return a value, which would be for each and for each ordered. And as you might expect, for each ordered will ensure in counter order. So it's a terminal operation that ensures in counter order, whereas for each does not try to preserve in counter order. So if you take a look here, you can see that the input as before is going to be 2, 3, 1, 4, 2. So that's all the same that we had before. In this particular case, we go ahead and are going to have an array list called results. This is not my preferred way of doing things, of course, because you normally would want to use a collector here, but I'm just showing you the difference between the for each ordered and for each methods. So in this particular case, the input's going to be ordered and non-unique. We create this output collection that'll store the results. And then what we do here is we use for each ordered, and we pass in the method reference results : add. So that's going to go ahead and add the elements into that array. Now, in this particular case, this is really subtle, the results will come back in counter order. So after we do all the processing, we'll have the results that will be basically 4, 8, 4. So that'll be the results, and that's the order that they'll show up in the results variable, guaranteed. And notice that also, even though we're using a parallel stream, we don't have to worry about race conditions here, because for each ordered has an implicit synchronization internally to ensure that there's no corruption of the data and that things get put in the right order. So this will work. It's kind of crufty. I would not recommend writing code like that, but I'm just trying to demonstrate the difference between for each ordered and for each. Conversely, if we use for each instead of for each ordered, then the results will come back in whatever order they happen to be processed in. And there's no effort by the framework, the streams framework, the parallel streams framework, in order to preserve that in counter order. Now, the other thing that's tricky here is that if you want to do this approach, you have to do a few extra things. In particular, before, you'll notice we used an array list and didn't worry about synchronization because that was handled implicitly by for each ordered. In contrast, in this particular approach, we're using the for each method, which says all bets are off as far as the ordering, but we therefore have to use a different data structure to store the results in. And that data structure has to have synchronized semantics on its add method. So in this particular case, we're going to replace array list with concurrent linked queue. And concurrent linked queue is a concurrent linked queue where the add operation is implicitly synchronized. So you can call it from different threads, and it'll make sure that the state of the concurrent linked queue is not corrupted in any way, shape, or form. So kind of subtle. I wouldn't recommend writing code like this in general, but if you must write code like this, be aware of the difference between for each and for each ordered. And also be aware that if you start using for each in a parallel stream, you've got to make sure that whatever you're collecting into or storing into, collecting is the wrong word, storing into, has going to have proper thread safe semantics for insertions and removals. But in particular, you need to do correct synchronized and thread safe insertions. Otherwise, chaos and insanity will break out. So that's the last discussion about the ordering of the results. So just to kind of briefly recap, you can't do much about the order in which the processing takes place, but you can control the order in which the results are placed back to you or passed back to you. And the typical way you do that is by using different splitterators, using different collections, using different operations, both intermediate operations, terminal operations, and so on, that will enforce in counter order in the results.